Alright, today we will talk about balance forces and zero torque. So in the previous video we talked about unbalanced forces, and today we'll talk about the balance situation, or in other words we'll talk about equilibrium. Alright, so it's in the same OneNote. So this is 4.2. We're going to look at also pulleys and suspended systems generally, but I want to run you through the condition of equilibrium, also frequently asked in paper 2. Number 1, you should have, or the system should have, no resultant forces. So no resultant forces here means net force is 0 lor, and also no resultant torque. Okay, so the net torque should be 0. Alright, but when you open up these two seemingly simple equations, what you will get, right, is that you will notice that there are actually a few ways to cut apart this. Now, whenever we talk about forces, it's a vector, so we need to be able to resolve them. And normally we will resolve them into vertical axis, so the upward force is equal to the sum of the downward force, or the horizontal axis. So the left force will be equal to the right force. Alright, and for net torque, we will do clockwise and anti-clockwise. This is moments, okay, which you have did some already in your IGs, if you did IGs. Okay, so we're going to do some examples lah, right? You write the condition no resultant force and no resultant torque, okay? Alright, so now this is a suspended system. You have a ball. I'm going to just draw out all the forces for you. Of course, because there's a string, there's tension. So you go through the list of 4 forces law. Got tension, got weight, okay? It is not touching any surface, so there is no contact force or friction, unless you consider air a surface lah. Alright, anyway, this is mg and the weight is 0.15 Newton. The airflow will push the ball in this direction. Okay, so I'm just going to call this force due to airflow F lah. If you want to know what kind of force this is, contact force also. Now this thing is suspended or in equilibrium. So I'm going to draw a vector diagram. You have tension, okay, pointing in roughly that direction. You know what? I think I'll just roughly draw a sketch lah, rather than pace and take time to do it. So again, to imitate the direction of tension, it will be roughly in this direction. Alright, and also at the same time, you will have weight pointing downwards. So it's going down, and your value of F is pointing in this direction. There you go. So whenever you have this cyclic triangle of forces, it means that the net force is 0 because there's no resultant. Okay, it goes in a circle. There's no result lah, you're moving in a circle. Make sense? So if you want to find the force on the ball, you can use tangent 30 lah. So tangent 30 is F over 0.15. Normally this kind of question you draw a diagram of forces is faster, especially when there's a 90 degree. It's always faster than resolving, because you got 2 unknown, T and F. But you can always form equation lah. One equation, use up and down force equal, left and right force equal, and try to solve. You can try. If you cannot do it, you can let me know. Alright, this one are very familiar if you did IG especially. Okay, so you have 2 masses at different position. Then she's going to put another mass at the 7 cm to restore balance, and they're asking you what mass should be placed at 7 cm. So basically, if you want to restore balance, the clockwise torque or the clockwise moment must be equal to the anti-clockwise moment. So as usual, I'm labeling all the forces, but since I know that the weight is directly proportional to the mass, I'ma just use mass as a placeholder lah, so to speak. Where it touches the contact, there will be a normal force. Okay. So because we don't know this normal force, we will use the fulcrum as the reference point. Okay. And for this unknown mass, it will have a downward force like this, but we do not know what the force is or the mass. So I'm just going to put the value of m in terms of gram. Okay. So now we can do clockwise is it's equal to anti-clockwise. By the way, there's also the weight of the ruler, but the weight of the ruler is uniform, so it's directly underneath the fulcrum. So the normal force and the weight has no torque or no moment. So I'm going to take that point, that big cross there, as your reference point. You know, as usual, you can always pause and try the question and then fast forward to see the answers. Anyway, clockwise would be your 50 gram. And the distance of... So this one is at 15 because it's 30 cm ruler ma. So 50 times 8, because 23 minus 15 is 8. And then 20 times 4. 15 minus 11 is 4. And we will plus mg times 7. Alright? Sorry, not 7. 15 minus 7, which is 8. Okay? So as long as the units are preserved, so you can see I just cancel off all the g, and then I will have m8 here, or 8m, and I can find my m. 320 divided by 8. 40 咯。80 32. 40. Alright. So in question 17, there is a slope, and your sledge will slide down the slope at constant velocity. And three forces acting on the sled is your normal force, weight, and friction. Constant velocity means equilibrium, so we are looking for cyclic triangles. So if you look at option B, the 2 arrow pointing out, wrong law. Option D, 2 arrow pointing out, wrong law. Option A, 2 arrow pointing towards each other, wrong law. So it has to be cyclic. The option is C. Very common past year. Okay, because you get the cycle. Cyclic. Alright. Okay, the next one is a popular question. You have a hinge trapdoor held by a cable. There's a hinge. The H is a combination of normal force and friction. Okay, so you're asked to give the three forces in increasing order of magnitude. So what I will do is, since this is in equilibrium, I will extend or try to extend all three forces because they have to meet at a single point. It might not be this magnitude, exactly this magnitude, but they will meet at a single point. Okay, so when they meet at this single point, I'm not sure what I'm trying to do here. Okay, hang on. The arrow is terbalik. Okay. So if you want to, if you're doing your homework on OneNote exam, I also don't know how. Okay, if you want to, what you can do is you can move the arrow a bit. You can see that these three arrows have to meet at a single point here before. If not, then it cannot form the closed triangle. Okay, later I'll pause the video for you to see. But now I'm dragging out the arrows to try to form a closed triangle. So I'm going to pause right here. And then if you look at this triangle, right, you will notice that, hey, the length doesn't really match. It doesn't matter because we are talking about direction. Okay, so some of it is an extrapolation, but the weight can normally be assumed to be constant. But either way, you can see that this one is the closed triangle as the vector diagram that we have drawn previously. sometimes the triangle, we have a fixed value, and then the forces we only know the direction, like H and T. So if let's say now you want to find increasing magnitude, you just the triangle. Okay, this extra part or you omit. If I'm drawing on the whiteboard, I'll use my hand to rub. Cannot. So we omit this part. So if we look at the triangle, the smallest value or the shortest length is W. So W is the shortest, okay, followed by the blue line, which is H, and then the longest one is T. You might be asking, exam time how? When you draw like that also, you can see W is the shortest. When you extend, W only extend a bit, okay, and then followed by H, and then T is the one with the longest arrow. So it will be W, shortest, followed by H, here to here, H, and T here to here. Of course, you can always try to transfer out when you actually have a physical paper lah. Okay. If not, you just agak lah. Slap a ruler on your computer. Okay? So yeah. So you're going to have the shortest one being W, followed by H. You can see even if you put here, you can see H is not as long as T. Alright. Okay, so now this one is also a fairly common situation. You have a load with a fixed mass. And what you're going to do is you're going to try to find a relationship between F and X. Now, if you want to maintain equilibrium, the torque must be constant because on the side of the fixed load, the load is fixed at a certain position, which means F times X is a constant. Okay, because this thing is in equilibrium. So if F times X is a constant, you are looking at the inversely proportional looking graph, which will be B lah. Alright, so or generally you can always test if X is bigger, like you move further away, you don't have to push down that much. Okay, whenever you carry heavy things, you know what I'm talking about. So right now, when F is small, X should be big, so C and D is out. You can use process of elimination. Okay, and then a linear is a bit hard to achieve lah. Okay, so what you can do is, like I said before, F times X is a constant. Alright, so if you don't know why F and X is a constant, I'll just write out the equation for you now. Okay, this A, let's say the distance A is fixed, mg is also fixed, so mg times A is constant. Mg times A must be equal to Fx. In this one, so F is inversely proportional to X, you get me though. Alright, this one, you have a negative charge in an electric field and a mass in a gravitational field. Okay, so sorry about the editing error. I ain't gonna edit again. So right now, to find the direction of force must be the same as the parallel to the direction of the field strength. So right now you can see F, field strength is like GPS for force. Okay, but the thing about charge, right, is that positive charge follow the field lines, negative charge go against the field line. Now I don't have time to put out another video for electric field in time for you, but you can watch Miss Elizabeth's videos about electric fields. Okay, so go watch. Anyway, your FE should be in the opposite direction to the direction of the electric field. If the charge is positive, then FE will also be pointing right. Okay, so yeah, so then your answer would be B lo. Okay, alright, moving on. Oh, this beauty. Okay, so now you are asked, this one is in equilibrium. Okay, so what to do leh? Same thing like the door with the hinge. we extend all the vectors. Basically, in the real world, pre-COVID-19, I'll tell my student to just draw dotted lines from the forces. Okay, but anyway, you will have a normal force. So they have a screw at S or R, doesn't matter lah. You get these three forces. So right now I'm going to do what I told you to do, which is to draw a line starting from S. Okay. And then starting from R and then from W. Actually, the good thing about doing this is that if you have one node like me, you can actually move it around so that you get a better understanding of the triangle of forces. But they all three supposed to meet at the same point, and you can see these three forces, they don't meet at the same point. R and S will meet at one point that is different than R and W, and that is also different than S and W. So A is wrong. They should meet at one. Three forces must meet at one single point. If not, you cannot form the triangle. If you don't believe me, you take these three lines and see if you can form a triangle for A. So I'm going to repeat the process again for B. All right. All right. Now for B, we are gonna. Hey, looks very promising. Although my W is a bit sangak now on hindsight. Never mind. Okay lah. This one C you look at it confirm cannot already. Who is going to balance your W? You got S to the left, you got R to the right. Nothing balance W. Okay, you're going to repeat this again for D. And at this point in time, I'm a bit lazy already, so I never bother to draw a dotted line anymore. I'm just going to roughly, hey, like got two answer leh. So I feel like, okay lah, maybe I should draw the lines properly. But you should also think about it, Okay? Even if both are okay, because they both B and D, boy and donkey, seems reasonable, but only one answer is acceptable, right? So which one are you going to choose? Question wrong. CIE is very rarely wrong. So the answer to my question is that if you look at D, you will notice that all the forces, so W is pointing down, S is pointing right, R is also pointing right. Who is pointing left to balance the right forces? Make sense? So there's no left force to balance the right force. Whereas for B, you have the S pointing to the left to balance R pointing to the right. Promising. Okay? Alright, now you have a guy using his bicep to hold a load, a 10 kg load. You're asked to find F lah, basically. Okay, so you have the weight of the forearm that the bicep need to sustain and the weight of the load as well. So I'm going to take that elbow, took me a while, elbow as a reference point and use clockwise moment is anti-clockwise moment. So clockwise would be your 20 Newton weight of the forearm. If you relax your bicep, your forearm will fall downward. Plus 100 times the perpendicular distance 0.32. That would be the force needed to be generated by the bicep multiplied by the distance from the bicep. So you curl, for the guns. Okay, then you can find F. The gamba, the diagram looks scary, that's all. It's a pretty doable question. Okay, right. This one. So here you have a spindle. Okay, so there are some dimensions that are given to you. You wrap the spring around the disc around the pulley on the string. Okay, and now you are supporting a 900 Newton weight. You are asked to find the minimum force at the end of the lever that can lift the weight. So you need to counterbalance the torque generated by the 900 Newton. Okay, so it's either you can visualize, or if not, then you would have to draw the forces a bit low. Okay. Okay, and by the way, right, both F and F are a couple. Okay, so now you have the force of 900 Newton pointing up. Okay, and you know, this tension here be linked to this tension here, and this tension will cause a torque on the disc, okay, of 180 Newton meter. Okay, this is due to the tension, and the tension is due to the 900 Newton weight. So the torque from F will have to counterbalance this 180. So I will take one of the forces multiplied by the perpendicular distance between the couple. Or you can F times 0.6 plus F times 0.6 is the same thing. Okay, and get 150 law of the equation. Okay, this one is a very common question. Every year people ask me. So now I try to solve it here, okay? So now you have a man on a motorized vehicle, and the vehicle has two wheels on one axle. Passenger stands on the platform between the wheel, and you have the weight of the machine 600 Newton in 600 Newton, 200 mm in front of the axle, okay, and the passenger will stand 200 mm behind the axle to balance. So the torque here now will be 0 until the motor moves. When the motor moves, there's a horizontal force of 90 Newton at the ground to move the vehicle forward. So I'm going to zoom into the ground, okay, and draw the 90 Newton. So the vehicle is moving forward. So if it's moving forward, the force have to be forward. Okay, the wheel push the floor backwards. The floor push the wheel forward. This is a friction force, parallel to the contact surface. You see, always the same 4 type of forces. I repeat, wheel will turn this way to push the floor backwards. It's like you walking on a treadmill lah. You push the treadmill backwards, the treadmill push you forward, kinda. When you walk on the floor, you push the floor backwards, the floor push you forward. Okay, anyway, enough rambling. Now we are going to take the axle as a reference point, and you want to know whether the man needs to lean forward or backward and how much he needs to lean. Okay, so we're going to take clockwise moment is equal to anti-clockwise moment. So obviously the 90 Newton will cause a rotation that is anti-clockwise. The weight of the man was also causing an anti-clockwise moment. Yep. And the weight of the motor itself, or the vehicle, will cause a force of a torque that is clockwise, 600 Newton. So we take 600 times 200 mm. This is fixed. Alright, 900 times 400 mm. This is also fixed from the ground. Plus 600 times x. Okay, so we can now find x. X is not the final answer. Remember, the man was initially 200 mm from the axle. Okay, so to reach 140 mm, he needs to lean forward 60 mm. Make sense? So 60 mm forward, so that he can achieve a distance of 140 mm from the axle. Okay. Alright, now let's look at this question. Relationship between force and momentum. So force is equal to the rate of change of momentum. And here you have a rigid bar of mass 450 gram, held horizontally by supports A and B. Okay, then you have the center of mass of the bar at point C. Assuming the bar is uniform, the ball is going to whack the bar at the corner, and then you get this velocity time graph. Fuyo. So here is the point where the ball hits the bar. How do I know? Because it slows down very quickly. You can see this part of slow down in one small box, and then down there is where it leaves the bar. Okay, here is where it leaves the bar. How do I know? Because again, the graph shifts. Okay, so is this short 2 boxes. This is your contact time. The time it took for the speed change from whatever value this is, it looks like 5.5. Okay, so it's the 2 boxes lah. That is your impact time. Okay, So the time taken for it to change from 5.5 to -4. So hit at 5.5, come up at -4. So to find the change in momentum, you take mv minus mu, final minus initial. Do not confuse, there are two mass. So the one we're talking about the ball, so 140 gram, which is 0.14 kg. Final speed is -4, initial speed is 5.5, so -4 minus 5.5. And this, ladies and gentlemen, will give you 1.33. Once again, the negative is for direction. You can omit and tick just the magnitude. If you feel very anal, you can just tell people the negative is which direction. Okay? So right now, you are asked to find the force. So the impact time is two small boxes. One small box is 0.02. So you divide by 2 times 0.02 lor. And you will get 33 Newton. Yay, proven. For the time the ball is in contact with the bar, find the normal force at support A and support B. Okay, these are contact forces when the ball is in contact. So when the ball is pressing down on the plank, so you have a normal force. Normal force is always pointed away from the contact point. Okay, so this will be NB and this will be NA, pointed away from the contact point. All right. Of course, you have the weight as well. The weight of the bar, 450 gram or 0.45 G, 9.81. Not the same G. 450 gram, 0.45 times 9.81. If you confusion, then you write 0.45 times 9.81. Okay, where the ball whacks the plank, you get 33 Newton of force. Force of the ball on the plank. Of course, the reaction force will be force of the bar on the ball, causing the ball to rebound. Okay, so what you calculated just now, the 33 Newton, let's go back here for a bit. The 33 Newton is the force that the bar exerts on the ball to cause the ball to change its velocity from 5.5 downwards to -4 upwards. Okay, so if the bar exerts a force of 33 Newton on the ball will exert a downward force of 33 Newton on the bar. Alright? Bar push the ball upwards, ball push the bar downwards. Alright? So now you want to find NA. So we will use point B as reference point. That way NB will have no torque. You do not want two unknowns. Ain't nobody got time for that. So this is 20 cm, 45 minus 25. So NA times 20. I'm writing here so that I can look at the diagram without scrolling up and down. Pening way, a bit dizzy. Okay, so 35 times distance from B, 75, 0.45 times 25. Okay. And then I roughly know this, and then I transfer down to here. Okay. So I'll get sum of the clockwise is equal to the sum of the anti-clockwise. So the clockwise will be NA times 20 cm from point B as reference, and NB here will have no torque. And your anti-clockwise will be 33 times 75 plus 0.45 times 9.81 multiply by 25, the distance from point B. You will now get NA. Ding ding. This force, this NA is only this value for that 0.04 seconds. Okay. And after that, it will return to normal. Pun intended. Okay, to find support, the force on support B, now you can use up force is equal to down force because you already know all of the forces. So your up force is NB, your down force is 33 plus 0.45 G plus NA. Ta-da! Okay, so then you can just substitute lor. Of course, if you want to make your life easier, you can always find what is 0.45 times 9.81 first. Alright, that will give you 166. Okay, so this is another example. You have a wall, you hang a bar here and then you tie a wire. Alright, the only value that they gave you, besides the length of the rod, is where the weight is. This rod is not uniform, and this force is 44 Newton. The tension is 44 Newton. Okay, and you are asked to find the vertical component of F. So to find this vertical component, we resolve again. So I think by this time in the revision videos, if you've been watching generally this stuff, you will notice that, wow, if I don't know how to resolve vector, every chapter also got problem. Correct. The only chapter you won't have problem is wave and electricities, because I don't think we need to resolve vectors there. Anyway, when we resolve this, the vertical one has no angle, so it's 44 cos 30. Then I'm just going to press my calculator. Alright, 38.1. Write your answers in 2 to 3 SF. Do not leave as 44 cos 30. So Fx will be 44 sine 30. That will be 22 Newton. Okay. By taking moments about P, find the weight of the rod. Well, I didn't leave space, so oh well, never mind. So this question is trying to be very helpful. Okay, so we are taking P as reference because there are two forces at P that we don't know. We don't know what the friction is, we don't know what the normal is. So I'm just going to draw here for you as a rough guess. Normal force again must be pointed away from the contact surface, so it will point in this direction. And friction, we don't know where friction is there. So I'm going to guess the friction is pointing upwards and assume that the end of the rod is about to slide downwards. This part here is about to slide downwards. Is it going to slide downwards? Well, actually later I will tell you how to see. Anyway, we choose point P because F will have no torque and will have no torque. Okay, the only torque you need to worry, and anyway 44 sine 30 will also have no torque because 44 sine 30 has no perpendicular distance from point P. It passes point P. So the only one with torque is W. Which one? And your 44 cos 30. That is all the torque that we have. Okay, because 44 is already split into 2. Alright, so we're gonna multiply now. W will cause it to rotate clockwise. 44 cos 30 will cause it to rotate anti-clockwise. So I'm just going to do the working here since down there no space. So W times 0.64 is 44 cos 30. Nah, be careful not 0.96 it's the whole thing. 整个 semua all. Okay, so 1.6 long. Okay, so we can find W . So basically, if you make your choice wrongly, or if the question is not so nice and it didn't tell you to use P, sometimes you got too many unknown, then you got headache. Or if there's a force and then you forget to include it, also headache. Okay, so yeah, go through the list of 4 forces. So you get 95.3. Explain why the wall must exert a force at point P. Well, look at the 44 sine 30. If there's no normal force, or who on earth is going to cancel off the 44 sine 30? It ain't going to be me, right? So you can just say opposing horizontal force directed away from the wall or to the right. Make sure you mention the direction is required to cancel out who? The horizontal component of your 44 Newton, or the tension in the string or the wire, or F. Okay, so this is 38.1 Newton, by the way, and this is 95.3 Newton. So the question is asking you, why is W 38.1 not equal to this one? So something is not right. Who is going to balance? You have an extra 95.3 here, You have a missing 38.1 here. Well, ladies and gentlemen, boys and girls, friction, no? This is how I know the friction is pointing upwards. This friction have to help the 38.1 to support the 95.3. Okay? 38.1 is not enough. Okay, so there's a friction because the weight will cause the bar to actually fall this way. Okay, this end of the bar is very likely to slide downwards. Okay, so we just move things around now. And then you can find your F. I don't think they need you to find F. But this is just roughly to show you if they ask you to find F, what to do. If they ask you to find the normal force is straight away equal to 44 cos 30, 22. And if they ask you to find the resultant between F and N, it should be 57.2 square plus 22 square. And again, you can see weight, the force from the wire and the force from on the wire and the weight and the normal force plus friction should meet at a point. Okay, so this is your arrow R, the R, to represent the force acting on point P, which is the resultant, sorry, not R, the value S, which is the resultant between friction and normal from point P. Okay, all three forces should pass a same point. Oh, good lord, what is this wire? Why is this so sangak? Well, life like that lah. Sometimes we get a normal year, sometimes we get COVID-19, sometimes we get a horizontal bar, sometimes we get a weird bar. Alright, define moment of force, product of the force and perpendicular distance, keyword perpendicular distance from a reference point. Don't forget that. So here we have a bar, but be thankful you got 90 degree. 90 degree is the best thing that you can see in a force diagram. Okay, so this bar is pivoted at the wall at point A. Okay, so I tell you at A there will be friction, there's likely to be friction, and it's definitely normal. Point A is the best point to use as your reference point or taking moments about that point. Oi, thankful lah. The question also try to help you lah, so you don't end up in Holland. You don't end up in Holland. Okay, so show that the T is 21 kilonewton. Okay, let's take moments about A. So we have a slight problem here because the distance between this 500 Newton and this distance is not perpendicular. If you want perpendicular distance, you have to this horizontal arrow and this horizontal direction. So mafan. So let me transfer the angle first, because whenever the force is not in the direction that we like, what do? We resolve. So we're going to resolve the 500 Newton and the 4000 Newton parallel to the bar, which will pass through A, then we can ignore. Perpendicular to the bar, where we can just take the length of the bar straight away as perpendicular distance. Okay. So when we split, this one is 400. There's no angle here, so 400 sine 30. There's no angle here, so this is 500 sine 30. Okay, 90 degree, which is why we can 500 sine 30 multiply by 1.4 and 400 sine 30 multiply by 2.8. So we can now use your clockwise is equal to anti-clockwise. So both 500 and 4000 sine 30 will turn the bar clockwise. Tension would be anti-clockwise. I'm just going to write the actual value because I already know 250 and 2500. Ding ding ding. Multiply by the perpendicular distance, so 250 is 1.4 meters away. Distance is now perpendicular. And 2000 is 2.8 meters away, and T is already perpendicular to God, so you just times 2.8. When you move some things around, then you get 2, 1 something. Okay, so this is about 2.1 kilonewton. Proven. Or you could be thinking, Miss, I'm very good at geometry. You see this red color right angle triangle? I can find this distance leh. Okay, now it's too small for me to draw an arrow. The arrow looks so ugly. Okay, anyway, I can find this distance. Then I can just take 500 times the distance from here to here. Okay, which is 1.4 sine 30 because you look at this triangle. Okay, and the distance from here to here, you look at this triangle, is 2.8 sine 30. Okay, so you can, and clockwise, which is p times 2.8, this is not a problem. Clockwise will be 500, this is 500 times 1.4 sine 30 plus 4000 times 2.8 sine 30. You will also notice that actually this is the same damn thing lah. I mean, sorry, excuse my French, it's the same thing. 500 times sine 30, 4000 times sine 30. No. Okay, so do whichever lah, as long as you're happy and you are confident that you know what's happening. Alright, so option 2, look for the perpendicular distance. Okay, now we're going to resolve t because the question is asking us to resolve t, I presume. Okay, so when we resolve t, this is 60 degree. The reason why we take a vertical, right, this is t cos 60, is because you are asked to find the vertical component. Okay, so I would like to just casually mention here, I mean, this one you can put 2100 or 2125, you get 1050. Okay, so I would like to mention here, right, that both green arrows, we take perpendicular to the bar because we care about the distance and we want to find the moment. So we are looking for perpendicular distance. This one we resolve up and down because eventually they're asking you to compare with 4000 and 500 newtons. So this red arrow have to be parallel to 4000 and 500. How you resolve is dependent on what you want to do in the question. Okay, don't go memorizing this kind of thing, try to understand. Okay, so you are asked why this 1050 is not equal to the load and the weight. So the load and the weight, right, okay, this TV, this load and the weight is actually 4500 and this one is just 1050. So why? Well, the beam is in equilibrium because the wall will exert an upward friction to help the 1050 counterbalance the 4500. Okay, so you can say there is an upward contact force, upward normal force. Hey, wait, not contact force. There's a force lah, basically resultant between friction and between the beam and the wall, and the reaction between the beam and the wall. I would actually say you can also just say that there's a force at point A. Okay, that has an upward component. They say vertical, so I put vertical, upward or vertical force. Okay, so if you want to score the other point, I've forgotten to write here, you should write TV in terms of this other force. So let's say you call this force A lah, FA. Okay, so when we look back at the diagram, give me a sec to rewind, what you can say is, there we go, you can say that TA, the vertical component of TA, or FA, so vertical component of FA is equal to 4500 minus T cos 60. Okay, again, up is equal to down, so FA, so let's say this vertical component here is FA. FA plus T cos 60 is equal to 4500. Okay, that is the second point. And with that, we have finished this video. Thank you for watching. I will see you in the next one, where we finish up chapter and talk about pressure. Till then, bye bye.